Welcome back to Ocean 201. We're going to be talking today about deep sea sediments, and we'll continue on later on in this section to talk about shelf sediments and then coastal processes. Our topic learning objectives are to be able to describe the processes that deliver sediments to the seafloor and where in the ocean they are important, to differentiate terrigenous and Terrigenous sediments and discuss their differences in distribution and composition, and explain different coast types and the natural and human impacts that can alter the coast. So the background image here is a picture of sediments taken on the continental slope off New England at a depth around 1,500 meters. And these are very fine sediments, and in the sediments you can see the tracks of these brittle sea stars. So what are sediments? Unlike the plate tectonic section where we were talking about the lithosphere and ocean and continental plates, these sediments are an accumulation of loose and unconsolidated particles. And these can be either organic or inorganic particles. Marine sediments can come from 4 different sources, either land through weathering, that can be physical or chemical weathering and erosion of rocks, or volcanic eruptions. They can come from biological activity in the ocean, chemical processes in the ocean, or from space. Now, one of the reasons that we care about sediments in the ocean is they can act as a record of what has happened to the world, and both in the ocean and also globally. So they can act as memory of the ocean. And this is an example from of a core in the western North Atlantic taken at a depth of 3,000 to 4,000 meters. I should mention sedimentation rates are very slow, and 10 centimeters of material can correspond. For instance, 10 centimeters here corresponds to about 100,000 years of deposition. So this core has been dated to about 65 million years ago, which corresponds to the KT extinction boundary. This is when dinosaurs were thought to have gone extinct due to the impact of a 10-kilometer wide asteroid. And so this, as you go deeper into the sediment core, you're going back further in time. So down at the bottom here, where we have this lighter colored gray material, this is before the impact, and in this material there's lots of biological organisms, small microscopic shells. We'll talk about them later, but from organisms that would grow in the sea surface, photosynthesize, die, and sink down and be preserved in the sediment. Now, the impact happened here, and then this is a layer of ejecta. So this is material that was blasted from the impact crater and deposited here within days to months. Now, after that, you get ash and fallout from the meteorite. There's an iridium anomaly that iridium is not common on Earth from terrestrial origin, but it is common in meteorites. And it's found, this layer is found all around the Earth at this time period. Right here, this material is basically free of biological material. There's mass extinction. Very little life is preserved in this sediment core, and it's really not until you get into, in this white area here, you have a little bit of sea life coming back, and then once you get into the gray area here, you're back to somewhat of a more normal life distribution of organisms in the sediment core. So this is an example of how we can use sediment cores to understand about the past history of the Earth and of the climate. And we'll talk more about that when we get to the climate change section at the end of this semester. But I wanted you to have some idea of one of the reasons why we look at sediments very carefully. Now, sediments can also be compacted and lithified into rock. We talked about the accretion of sediments as ocean plates subducted underneath each other and underneath continental plates. And so that can, ocean sediments can eventually go on to become part of continental crust material. So where are the sediments? So the continental margins contain about 87% of the volume of marine sediments, despite the fact that they only occupy about 21% of the ocean area. So in this table, it says the distribution average thickness of marine sediments. On the continental shelves, slopes, and rises, which comprise, as I said, 21%, about 87% of marine sediments, and you can get up to 9-kilometer thick sediments in these regions. On the slopes, you get some of the thickest sediments, and as we talked about before, that can be in part due to accumulation accretion from plates going underneath one another, but that is more so due to the fact that the land is the source of many of the sediments in the ocean, and the continental shelf slopes and rises are obviously next to the land, and so that's where you get a lot of sediment being transported from the land into the ocean. Whereas deep ocean floor makes up about 78% of the ocean area, but only about 13% of the total volume of sediments, and they're much thinner there as well. So you can classify sediments on a number of different properties. Marine geologists will pay a lot of attention to sediment size, so everything from boulders, cobble, all the way down to sand, silt, and clay. From a size perspective, it's important to know that larger sediments will essentially sink, not instantly, but they'll fall without much delay to the bottom of the ocean. Whereas once you get into the sizes that I've highlighted in red here, these can take days to decades to settle. So sands will take about 2 days to settle, 4 kilometers, which is about the average depth of the ocean. Silts can take on the order of months, and clays up to decades if they settle at all. Also can talk about the source of sediments, and that's what we're going to focus on more. So you can have terrigenous, biogenous, cosmogenous, or hydrogenous sediments. Talk about these differences in a second. You can also talk about the location, either neritic, near shore, or pelagic, meaning offshore. So as I said, we're going to focus more on the source than on the size or the location of sediments. And in large part, that's because that is what has a bigger impact on the chemistry and biology of the ocean, and so ties in with the sort of overarching view of the ocean that we're trying to give you in this course. Now, size can be very important in terms of sorting and understanding layers in the ocean. We'll talk a little bit about that when we talk about terrigenous sediments, but for the interest of time, we'll focus on the source. Okay, so when we're talking about source, so we have terrigenous, biogenous, hydrogenous, and cosmogenous, as I mentioned. Terrigenous and biogenous sediments make up the vast bulk of marine sediment. So almost 100% of marine sediments are terrigenous and biogenous, whereas hydrogenous and cosmogenous are only about 1% or less each. Terrigenous sediments come from the land, so that's erosion of the land, quartz, clays, estuarine mud are all from the land. It's dominant on continental margins and abyssal plains, and they occupy about 45% of the ocean floor area. Biogenous sediments are those that are comprised of essentially the leftover or dead parts of phytoplankton and zooplankton and other biological material that grows in the ocean. So it's a combination of organic matter and hard skeletal parts of marine organisms. The examples, we'll talk more about this later, but calcareous and siliceous oozes are what we call sediments that contain large proportions of either calcium carbonate or silicon dioxide, and these are dominant on the deep ocean floor. There's a depth dependency that we'll talk about more, where you have siliceous oozes below 5 kilometers and calcareous oozes above, but these are deep ocean sediments. Hydrogenous sediments, or authigenic, is another way that we commonly describe them. That means that they form in place. And so this is the precipitation of dissolved minerals. This can be mediated by bacteria, but we're not talking about skeletons, bacterial skeletons. These are just, it's a chemical precipitation, and bacteria can make that go faster. Examples here, manganese nodules, phosphite deposits. It's a very important right now. There's a lot of deep sea mining that is being proposed and explored. And so that's important to understand about those. And they're present with other more dominant sediments. And cosmogenous sediments, we're not going to talk too much about those today. This is dust from space, meteorite debris. We talked a little bit about that in KT extinction. These are tektite spheres or glassy nodules. Essentially, they're distinct in both their origin and also they melt as they come through the atmosphere, and so they can be pretty distinctive. But they're not incredibly important to most of our large-scale understanding about the ocean, so I'm not going to get into those today. So terrigenous sediments, they're part of a very slow but important cycle. And this cycle, actually, the weathering of sediments and transport back in the ocean, this is one of the large cycles that helps to regulate climate. We'll talk a bit more about that in the climate section. But as you know, we talked earlier in plate tectonics about how we can have this accretion of sediment as ocean plates subduct underneath continental plates. And you get these sedimentary beds that form. And then, so you then have uplift, creation of mountains, but then that sediment is transported back through physical and chemical weathering into the ocean, where it's deposited along the ocean shelves and then transported down into the ocean at depth. So how do terrigenous sediments get into the ocean? There's a number of ways. We're going to focus on a few of these just briefly. So rivers, most terrigenous sediments are transported into the sea by rivers. Here's an example from the Mississippi River Delta. You can see that the river is quite brown from all that sediment load. These flow into the ocean, and right here you can actually see how this is building out land as that sediment is deposited and extending the delta out into the ocean. 3 rivers account for most of the sediment input into the Atlantic Ocean: the Amazon, the Congo, and the Mississippi. These are a huge source of sediment to the ocean. You can also have turbidity currents that take sediment from near shore down to deeper depths. We'll talk about those in a minute. Hyperpycnal currents, we won't get into detail here, but essentially river outflow that has enough sediment can pour down into the deep ocean. So when you have fresh water coming in the ocean, fresh water is less dense than salt water. You'll learn more about density in physical oceanography later on in the semester. But the lighter fresh water can get actually denser than salt water if it gets enough sediment in it. So as you load sediments in the water, that water gets denser, and if it gets dense enough, you get a hyperpycnal current, which essentially means that as a river flows out into the ocean, it immediately sinks down and transports a lot of sediment down into the ocean depth. Wind deposition can be very important. You might not think you get that much transport, but some of the dust and ash that's transported by wind contains a lot of nutrients. And then also ice rafted sediment can be quite important as well. So turbidity currents. This is a interesting and important way that sediments can get transported from the continental shelf down into the deeper ocean. So rivers and nearshore processes can take sediments into continental shelves, and these can be very unstable piles of sediment. And so you can have some disturbance, earthquake, or just enough sediment accumulates that you get movement, and that movement then can be very rapid and have essentially an underwater mudslide. It can be fast moving, so multiple hundreds of kilometers per hour. So really sort of hard to imagine, but it's essentially what we would think of as a landslide, but happening underwater. And so that transport can result in this deep sea fan of sediments. And they can also then produce submarine canyons above. And so this can add a lot of features to the continental shelf and nearshore environment. And these are important to our understanding of sediment cores and ocean sediments because they can form turbidites. And essentially when the material is deposited, the flow deposits the sediments in different layers. It sorts out the material based on the size. So in the very fast initial high energetic event, only the coarse materials are laid down. The finer materials don't settle until later when the flow slows down. And so you can get this layering that reflects these repeated turbidity current events. So wind deposition, like I said, you can have really important dust deposition. So this is Saharan dust coming into the Atlantic. Here is evidence, or is ash from Kilauea, the volcano depositing sediment into the ocean. And you can actually, you can see the impact of this dust. You can trace metals in the dust into the ocean. And the metals that get transported, iron is really the primary one, fuel a lot of biological production in the ocean. So a lot of the ocean is limited in micronutrients, so things like iron, and this dust can actually then allow phytoplankton to grow when the dust settles on the ocean surface. Similarly, volcanoes can stimulate biological production. There have been a number of studies that have shown blooms that result directly from the fallout from volcanic eruptions. And then finally, ice rafted transport of sediments is important. So as glaciers flow on land surface, they scour the land beneath and incorporate a lot of those sediments. Those can get transported out to sea when the glaciers calve off and enter the ocean. Or sea ice can transport out. So sea ice is free floating, glacier is bound into the sediment. Sea ice can accumulate dust on top, and then when that sea ice melts seasonally, it deposits a lot of sediments in the ocean that can stimulate biological production. So I do a lot of work in the Southern Ocean around Antarctica, and one of the things that we look at is the seasonal bloom that occurs as sea ice retreats. And part of that is due to relieving light limitations. You get sunlight into the water that was previously covered by ice, but part of that as well is the release of nutrients in that dust that is accumulated on the ice. So we're going to leave off for now there. We'll come back next time to talk about biogenous sediments and get into those in more detail.